Okay, let's talk about spin. Spin, why we need it. Spin is strange. It's um, it's mostly only understood by metaphor, but at the same time, it's real. So how do we know we actually need it if we can't see an electron spinning on its axis? Well, we know from experiment that electrons, for example, in the hydrogen atom, when they relax from n equals 2 to n equals 1, then they'll emit light. And for the hydrogen atom, if you look very closely, this transition is split into two lines. So 82258.921 versus 82259.287 inverse centimeters. So about a third of an inverse centimeter is a splitting of that peak into a doublet. And how do we explain this experimental result? Spin is the model that helps us explain why this splitting happens. So here's the idea. In our model, we say, well, there's an angular momentum that's due to the orbit of the electron around the nucleus, the orbital angular momentum. That's the movement of the electron around the nucleus. But then there also, in our model, is a magnetic moment from the spin of the electron. So you could, here's the metaphor, nobody can see this because electrons are too small, but the metaphor is, as an electron is moving around the nucleus, and that has some angular momentum to it, and it's a movement of charge, so then that will have a magnetic dipole associated with flow of charge around an orbit. As it's doing that, the electron also is spinning, in quotation marks, on its own axis. And of course, that's also a flow of charge because this is a charged object and it's moving. And so then by the right-hand rule, if that were counterclockwise, it'd be spin up, or if it were clockwise, that would be spin down. And then those two magnetic moments might be aligned with each other, parallel, where North Pole and North Pole are both on one end and South Pole on the other. Or they could be anti-parallel, where North Pole and South Pole are next to each other and vice versa. And then those would have different energies, and then that would account for this splitting. Well, that's the metaphor. How it's derived in the model is it only really shows up if you look at relativistic quantum mechanics, and Dirac did this in the 1930s. There's no correspondence principle for spin. We talk about spin being up or down. So m sub s, this is the spin magnetic quantum number. It can be plus a half or minus a half. And there's no classical limit to this. It's not a classical concept, so there's no correspondence principle. Notation-wise, it's analogous to the orbital angular momentum equations. So, as far as the wave function goes, we could have a 1s wave function would spin up, and that would be psi 1, 0, 0, 1 half for spin up. So 1, 0, 0, our notation here is 1s. So n equals 1, l equals 0, m sub l equals 0. That's the 1, 0, 0. And then spin up m sub s equals plus a half. So this is equal to 1 over square root pi times 1 over this, just a normalization constant, e to the negative r over a naught. And then alpha is this spin wave function component. And alpha is the spin up wave function. Beta would be the spin down. And that's the whole extent of the equation. There's no functional form to alpha or beta. It's just spin up and spin down. So then for the total spin angular momentum, this is going to look exactly analogous to the total orbital angular momentum. So instead of capital L squared operating on our spherical harmonics to give us h bar squared l plus 1, we're going to do the exact same thing except capital S squared operating on our spin eigenfunction. So that's our operator eigenfunction. Eigenvalue is h bar squared, and this just is analogous to down here. So we have the spin quantum number s times s plus 1 alpha. And our quantum number, our spin quantum number, can only be a half. And that's the magnitude of the spin angular momentum quantum number. So when you plug it into the equation, you get 3/2 h bar squared alpha. Similar with spin down, still s is a half. For the spin on the z-axis, this is going to be the same as the operator that we saw with the orbital angular momentum, the z-axis. That gave us our m sub l quantum number, and this will give us our m sub s quantum number. And that can be either plus a half or minus a half. So s is analogous to L, and that's the spin quantum number. M sub s is analogous to m sub l, and that's the z component of the spin, and that's the magnetic quantum number, and that's the z component of the orbital angular momentum, or the magnetic quantum number for the orbital. All right, so anyway, these equations really are just definitions. You can't do this math. There's no functional form to alpha or beta, so there's no math to be done there. They're just really definitions. Same thing with orthonormality. So you could take the integral of alpha star alpha d sigma is spin space, whatever that is. I think that's, when you're nauseous or something, you're in spin space. But if you integrate over spin space, alpha star alpha, beta star beta, either one, you get 1. That's normalized. But if you do alpha star beta or beta star alpha, you get 0. And that means it's orthogonal, so those two things taken together, orthonormal. So again, I've said it a few times now, these equations are just definitions. Alpha and beta do not have a functional form. All right, so for example, 1s orbital, we talked about this a little bit already. So n equals 1, L equals 0, m sub L equals 0, and we could do the spin up, m sub s equals plus a half. Then our psi 1, 0, 0 half would be this, where this is a capital Z here. So we could, with the hydrogen, that's just going to be a 1. Or we could have spin down, and the only difference is alpha versus beta. Now our Hamiltonian has to change if our energy is going to be slightly changed. So we got basically the same first two terms, exactly the same first two terms. We got the kinetic term, potential term, and then the spin-orbit coupling term. And this will account for the coupling of the orbital angular momentum and the spin angular momentum. It's a dot product of those two operators. Here we could do some math, but we're not going to for now anyway. And this is just alpha is a new constant. This is called the fine structure constant, which to a good approximation is just 1 over 137. It's dimensionless. You can get it from fundamental constants here, where we got the charge on the electron squared over 4 pi epsilon naught, permittivity of free space, h bar, and speed of light. Lo and behold, put all that together and you get 1 over 137. Anyway, the number 2 and then r cubed, that's the distance, again, to the electron. But once you put this term on, alas, the Schrödinger equation for the relativistic hydrogen atom cannot be solved exactly. Oh man, so even for our simplest real system of all, once you include relativity, we can't solve the Schrödinger equation. Never fear, we'll be able to get really close. And as you saw, the relativistic effect on the energy is tiny as far as, compared to the total value. Okay, so another thing that's important about spin is how it informs the structure of the periodic table ultimately via the Pauli exclusion principle, which comes from the Pauli principle. So This is kind of review from Chem 103. You probably heard that no two electrons on an atom can have the same set of 4 quantum numbers. I'm sure you heard that. Maybe your instructor called it the Pauli exclusion principle. That's what it is. So the 4 quantum numbers, of course, are n, l, m sub l, m sub s. So in other words, only 2 electrons can occupy an atomic orbital. You could have one spin up and one spin down. Or another way to put it is only 1 electron can occupy a given spin orbital, so the full wave function with the spin. Now, where does this Pauli exclusion principle come from? It comes from the Pauli principle, which is a postulate of quantum mechanics. So the Pauli principle is wave functions must be anti-symmetric with respect to the interchange of 2 electrons. What? Okay. So let's take a look at that, but first we have to talk about the principle of indistinguishability, and then that with the Pauli principle will lead to the Pauli exclusion principle. So experimentally we know that all electrons are the same. They're indistinguishable from each other. So we can't say, oh, look at the first electron compared to the second electron. Like they have to be equivalent to each other. And believe it or not, this has implications then for how the model works out, and it leads us to the Pauli exclusion principle. So let's look at an example. So let's say we had a helium atom in the hydrogen atom approximation. So we're going to use the solutions to the hydrogen atom Schrodinger equation to give an approximate form for our helium atom wave function. We do this kind of thing all the time. So anyway, an eigenvalue could be, for the 2 electrons in the helium atom, psi 1, 2, would be 1s alpha 1, 1s beta 2, so electrons spin up and spin down in the 1s orbital. And 1s alpha 1 is just this z cubed, which is going to be, now z is equal to 2. A naught cubed pi to the 1/2 e to the blah blah blah, right? So that's the same thing that we had up here. Oh, except maybe that z is not supposed to be cubed. Anyway, other than that, it's the same. There's an error either here or up there. I'll figure it out. Okay, and then, or we could have another eigenvalue, 2, 1, where we have electron 2 spin up and electron 1 spin down. But because of indistinguishability, really these two wave equations, even though they are eigenvalues, they are solutions to the Schrodinger equation. Because of indistinguishability, we need a linear combination of these two, because we can't say that electron 1 is spin up and electron 2 is spin down or vice versa. They have to be the same. They have to be indistinguishable. So we can take a linear combination of these two, and we can either add them together or we can subtract them from each other. And this 1 over square root 2 is just to keep things normalized. Then, if we look back at the Pauli exclusion principle, however, which is that, no, the Pauli principle, wave functions have to be anti-symmetric with respect to interchange of 2 electrons. So if we change 1 and 2 around in the psi 1, 1, 2, we'll get the exact same thing, because spin up, spin down, 1, 2, spin up, spin down, 2, 1. If we change these labels to 2, 1, that just turns this first term into that term. And if we change these two labels 2, 1 to 1, 2, that turns this second term into this first term, and they would just be equal. But on the other hand, with psi 2, if we change 1 and 2 to 2 and 1, then that would be positive this second term, and similarly this negative term. If we change 2 and 1 to 1 and 2, that would be negative this first term. So then psi 2 is equal to negative psi 2, 1. So really this psi 2 is the only one that works. It's the only acceptable wave function. These two aren't acceptable because they don't have indistinguishability. This one is not acceptable because it doesn't have doesn't follow the Pauli principle, so only this one is allowed, psi 2. Okay, and then finally, how does this lead to the Pauli exclusion principle? Well, this would not be true. Psi 2 would not be allowed if both electrons were in alpha or in beta. So if both of these were alphas, then it wouldn't be antisymmetric anymore, or if they were both betas. So we can only have 2 electrons in the 1s orbital for the helium atom. And if we went on to lithium, we wouldn't be able to put a third electron in there, and therefore we have to go to the 2s, and that's the Pauli exclusion principle, and that's the principle that helps us build then the whole periodic table. All right, that's it for spin. I hope you're all doing well. Sorry I can't see you in person. I will have office hours on Thursday, so maybe we can talk some more then, and you can ask questions.